All right, folks, I think it's about time to get started, and we'd like to start right now by saying thank you so much for joining us. We would actually like to start by introducing Sean O'Brien, the President and CEO of NABCEP. Welcome, Sean.
Thank you, Justine. And NABCEP is very privileged to be working with Mayfield Renewables. We've had a relationship with Ryan since, I believe, 2011, delivering updates and very vital information on the NEC code. We've seen that class at our conference grow from maybe 100 folks. I think last year we had 250 of our attendees, which is about half of our attendees attend that class. So it's a very important class. Going forward, with the pandemic, NABCEP is moving, as you can see, to a virtual conference. We will expand it from 4 days to over 2 weeks, just about 2 weeks. And the reason for that is we want to make sure everyone's able to be able to attend all the coursework and technical trainings that happen during the conference. Generally, an individual will be able to have the opportunity in person to get about 21 hours of continuing education. What NABCEP is doing this year, it's with the platform we're using, it's not a one and done. We were actually going to allow all the attendees to have access to the platform for a year. So in reality, you'll be able to, if you go back and look at the recorded technical trainings, panel sessions, and the all-day sessions, including Ryan's class, about 106 hours of continuing education. So we're excited about it. We decided to go something with a platform that is long-term instead of just a one-time thing. So it's something that we think will benefit the certified folks with NABCEP and folks who are looking for training to become certified. It is something different for all of us, but this is something actually NABCEP's going to continue in the future. We're looking at that we will do not only in-person conferences in 2021 and beyond, but during those conferences, we're going to start offering a virtual component so that everyone can, regardless of where you are, be able to take advantage of all the technical trainings.
Great, thanks so much, Sean. All right, well, we're going to go over a couple of housekeeping rules. We have the Zoom platform, which I'm sure many of you are familiar with at this point during the pandemic. A couple of features we want to point out, in particular the chat button on the bottom. We're going to be using that to post links or comments throughout the presentation. So if Ryan discusses something that we feel there's an additional resource for, we'll post that link on the side. And then because everyone will be muted throughout the webinar, we would like you to use the Q&A feature on the bottom of your screen to post any questions you have. And we have about 10 minutes at the very end to go through those questions and answer them. If there's any additional questions that come in that we don't have time for, we can follow up with you after the webinar. So the first thing we'd like to do is introduce ourselves, Mayfield Renewables, which was established in 2007. And we have several different facets of our business, our design services, which is plan set design, or plan set creation for commercial and industrial and utility scale solar and solar plus storage projects. We've also been building up our team of educators and technical writers to launch our technical services line, where we produce webinars such as this one. We offer white papers and competitive market research. Basically, we are aiming to bridge the gap between engineering and marketing with our new materials. We like them to be easy to understand and engaging for your clients. And we also have an education line, which we are most notably working with NABCEP for the NABCEP CE conference that we just discussed. So our featured speaker today is Ryan Mayfield, our founder and CEO. He is definitely an industry expert in the National Electrical Code and PV system design. Ryan was a technical editor for Solar Pro magazine for many years, from 2010 until 2018, when that publication ceased to be published. And obviously an NEC trainer at the NABCEP Conference. So if you've been to any of those conferences, you're probably familiar with Ryan and his courses there. So we're really excited to have Ryan basically instructing us today. And this is a teaser. This course we're giving you, this webinar, is a teaser to a longer format course at the NABCEP Conference coming up, which I believe is a 6-hour course. And so Ryan, you can take it away.
Thanks, Justine, and thanks, Sean, for doing the intro for the NABCEP conference. And so, yeah, for those of you that are interested in the NABCEP conference, if you haven't been before, I highly recommend it. It's always been my absolute favorite show to go to. So unfortunately, in our current state, in our current world, you know, we're not getting to do these in person, but just the presentations, the attendees, just everything about the NABCEP conference was always such high quality and high caliber. I've always felt very lucky to be involved. And so I actually, yeah, so Sean was, as you were saying how long I've been involved, I've been teaching the code course from the very beginning since the CE conference started. And so for those of you that if and when I see you again in person, ask about the first conference in Malta. I have a great story about a turkey and one of the attendees. It was kind of a crazy story, but that just, when Sean mentioned that was exactly where my head went, was this, the conference in Malta. So good stuff all around. So yeah, highly recommend that if you have the opportunity to attend the conference, that you do so. So as Justine mentioned, this is, pretty short form. We only, have 45-ish minutes here to go through some code stuff. So I picked out kind of the highlights or some of the highlights, I think, of what code changes and the current code, some of the both 2017 and 2020 updates. And so we're in one of those funny years, in the sense that code NEC comes out or has an update every 3 years. 2020 is one of those years. And so we have this break of some jurisdictions are still using 2017, some are moving on to 2020, some are just getting ready to adopt 2020. So there's a lot of just, I would say, kind of moving parts here in that sense. So if you are not sure what your code cycle is, then I would recommend either checking with your AHJ, but there's also, we can post this link in there. NFPA has a link to what the adoption is for the different code sections. So you can take a look there and see exactly where your code section is, or where your code cycle is, excuse me. Nonetheless, I want to get into, so part of the reason why we have to do both 2017 and 2020 is because of that. California just adopted 2020, pardon me. California just adopted 2017 at the beginning of 2020. Other locations like Massachusetts are already on 2020. So the adoption rate's different. And so I want to point out kind of those different, the differences between the 2 years as we're going through. So again, highlight, we'll go through 690.1 today. We'll talk about some system component configuration. Specifically, I want to talk about PV system disconnects. 690.7, there's some stuff about maximum voltage. Some things haven't changed that I'm going to point out, and then there are some new things in 2017. 690.8 goes right along with 690.7, so we'll talk about some of those changes, and there's a new, pretty big new one in 2020 for 690.8. And then I'm going to leave 690. There's a whole bunch of stuff. You'll probably notice the whole grounding and bonding is getting omitted here. Don't worry, we'll talk about it at length at the conference. There's plenty to talk about, but it could have turned into a 3 or 4 hour discussion if we wanted to. But going to jump out of 690, jump into 705. In the 2020 version of code, there is a brand new section, 705.11. It's called supply side source connections. And so we'll talk a little bit about that, talk a little bit about 705.12. It's called point of connection in 2017. and they changed the title of it to load side source connections in 2020. So that's my goal, to get through those and be able to talk to you about all those different things. So the first thing I wanted to go about, or to talk about and go through, is the 690.1 images. And so if you have your code book with you, either 2017 or 2020, I highly encourage you to follow along. And 690.1, they included some new images starting in 2017, which are very, very helpful. Those images probably haven't changed since 1984, when code was first introduced, or when the PV section, when 690 was first introduced in code. My earliest code book, I think, is like 99 or maybe 96, and the images were the same there. So got some new images. We took what you're looking at on the screen here is we took the code block diagrams and spruced them up a little bit, trying to make them a little bit more interesting. And so that's what you're seeing here on the screen are these images from 690.1b. Before I jump too far into it, one of the things I harp on this quite a bit, and so I'll mention it right now, is when you are looking at the code requirements and looking at different definitions, things like that, it's always helpful to go back and look at actual definitions for different components or different systems, things like that. And so PV system is actually one that seems like maybe it's, if I say define a PV system, probably everybody in the audience has a definition that's probably pretty close to what the code definition is, but it may not be exactly what it is. So that's why I highly encourage you to go look at that. And I've had these conversations with jurisdictions, inspectors, for example, and I've talked to them about the PV system disconnect, and they're like, well, what is a PV system? It's not even really defined. And well, actually it is. It's in Article 100. And so if you go back to Article 100, look at the definition of a PV system. This is paraphrasing some, so you can go look at it, but essentially it's all of the components required to convert solar energy into electrical energy. And so that's what defines our PV system, is all of those components. And so pretty obvious, that the solar modules are part of that system. And then what we need to do is we need to then evaluate everything else as far as what are those components that make that system. And the reason why I talk about that and get into this is because of that PV system disconnect label there that we have. So on the screen here, what we're looking at is a just really straightforward, simple grid tie system. Not showing you, I'm not saying these are all the components. I'm not saying that, there may be optimizers, there may be other components here, but this is, I think, gets you the kind of the big picture of what this is. So we have our PV array going to an interactive inverter, and then tying into a main panel in this case. So again, this is probably a very common residential type system. And so what we need to do is we need to define what is the PV system disconnect. And so you see that image there and you see the label. And honestly, that disconnect, that knife switch may or may not be a requirement for your system, depending on the location of the inverter in relation to the main panel, depending on the rapid shutdown requirements. All those things are going to come into place. What the utility, beyond code, the utility may have a requirement. So I'm not saying that knife switch is an absolute requirement, but it could be, and that would be considered the PV system disconnect. And the way that that's been explained to me, and I like to think of it this way, it seems to make some sense, is when you're standing at that disconnecting means, if you look upstream towards the PV array, towards the source of power, is all that equipment required to convert solar energy to electrical energy? So is it part of the PV system? And then similarly, if you look downstream, in this case towards the utility, is that equipment required to convert solar energy to electrical energy? So in this case, we're standing at that, what's labeled the PV system disconnect, and you throw that disconnect, you open it, all of the equipment to the left towards the array upstream, that is all required to convert solar energy to electrical energy. The equipment downstream doesn't require the solar array. So we have our PV system disconnect. And again, that night switch may not be required, so you actually could use the breaker inside the main AC panel in this case. That could serve as the PV system disconnect as well. So that's kind of the easy, I would, quote unquote, easy generic interactive system. Now I want to show you a couple others that are more complex, and just to show you how the PV system disconnect can move around a little bit. So realize there's a lot going on this image. So what we're looking at is a DC coupled multi-mode system. And so the PV array is coupled with the inverter, the multi-mode inverter in this case, on the DC side. And so again, this kind of gives me an opportunity to go back, and if you're not quite sure what a multi-mode system is or a multi-mode inverter is, go back and look and see how code defines multi-mode. And it's an inverter or a system that can operate in both grid interactive and standalone modes. So this is a standard backup type system. So we're seeing a lot of these systems more and more. We're seeing with the public safety, power shutdowns, PSPS. We're seeing those in California quite a bit. And so we're seeing storage in more and more in our systems as a whole. Now, the big question here is, where is the PV system disconnect? And while we're not going to talk about rapid shutdown today, this definition, this location of the PV system disconnect is pretty important, because it does have a direct correlation and a direct relationship to rapid shutdown and what is required for rapid shutdown. So for a DC coupled system, this becomes pretty darn important. And so you can see we already have it labeled there from PV array going to a PV system disconnect, going to the multi-mode inverter. And again, the explanation, the definition I was talking about before is, when you're at that disconnect and you look upstream towards the source, is all of that equipment required to convert solar energy to electrical energy? And then conversely, look downstream, is that equipment required? So, and again, this is not an all-inclusive diagram. There's likely going to be charge controllers, there might be some optimizers, those kinds of things. But nonetheless, when you're at that, what we're calling the PV system disconnect, and you pull that disconnect, you open it, then you've isolated the PV array from the multi-mode inverter. And then if you look downstream at that multi-mode inverter, none of that equipment's required for the PV, for this PV system to convert solar energy to electrical energy. It's a good design practice, and it's the way you would want it to be interacting with all that, but it's not required. The energy storage system can still work with the multi-mode inverter, back up that panel, interactive with the utility. So the PV system is not an absolute requirement for the rest of the system. So that's why the PV system disconnect is over there on the DC side in this case. So when we're talking about these and when we're looking at these, it's not, you can't just say the PV system disconnect is the AC disconnect for the inverter or the DC disconnect. It's dependent on the system that you are working with. So it's important, again, what are those definitions? How does this apply? And where does that fit in? And then the last slide I want to show you as it relates to 690.1b are these AC coupled multi-mode systems. And in this case, you look at the top of that, this diagram, and that's the grid interactive system. Essentially, that's all those same components: PV array, interactive inverter, PV system disconnect. In this case, it's getting tied into a backup panel. And then we have our multi-mode inverter over there on the left. So again, what are all the pieces of equipment required to convert solar energy to electrical energy? And in this case, because we're doing AC coupled, and we're not going to get into the advantages, disadvantages, it's not really a design class, but just recognizing that there are different ways of coupling the the solar system with the rest of the electrical system on the AC side or the DC side. And so in this case, the PV system disconnect again moves to the output of the inverter, of the interactive inverter, that is. And so again, we're back on the AC side of the system. And so those are some things that we need to consider for the PV system disconnect. and I realized I hinted at it, but I didn't say it, so I'm going to go back real quick to this DC coupled system. And as it relates to rapid shutdown, the rapid shutdown requirements are for the PV system conductors. And so that's why I spend so much time talking about what is the definition, and define what that PV system disconnect is because now you have that PV system disconnect, you've contained essentially what the PV system is, and now those are the conductors you have to control, not the energy storage system, not the backup system. Those are not part of the PV system. They've actually got pulled out of, energy storage really got pulled out of 690 in 2017. So it's not there anymore. So that's not considered part of the PV system. So in that sense, I know rapid shutdown is not necessarily contentious anymore, but it's, in that sense, it's made the rapid shutdown part of a DC coupled system more simplistic in terms of what are the conductors I have to control. So I wanted to just point that out. Okay, so I want to move on to 690.7 voltage limitations. This is not really new on either 2017 or 2020, but I kind of want to set the stage. And there is a lot of gray text in 2017 when it comes to 690.7. So I'd like to point out, so if you're not familiar with the way code is set up or laid out, if you're just kind of getting into it now and you have your code book, you see a bunch of text that's highlighted gray. I'm not really sure what that means. That's a language that has changed from the previous, or a section that's changed from the previous code cycle. So if you look at 690.7, there's a bunch of gray stuff there, either added or deleted. If they delete sections, it's marked. If it's new, it's marked. So there's ways of telling what has changed from one code cycle to another. So in 2017, there's a bunch of stuff that's grayed out. And sometimes they just grayed out even if it's been slightly modified. So you have to kind of realize. But nonetheless, voltage limitations for our 1 and 2 family dwellings is maximum 600 volts DC. So that's our temperature adjusted DC voltage can't exceed 600 volts. That's been that way for a long, long time. So nothing new there. For other types of buildings, anything that is not a 1 or 2 family dwelling, the limitation is 1000 volts DC. So if you're on a building, your system, maximum system voltage, so the voltage between any 2 conductors, if you take your meter, between any 2 conductors in the system can exceed 1000 volts. And then for systems that are not located on buildings, and so the question that comes up a lot is, well, what is a carport? Is a carport considered a ground mount? Do I need my 1000 volts, 1500 volts? And in my mind, carport is not on a building, but again, that's a question you want to verify with your AHA. I've had some AHAs just really dig their heels in and just stick to that for the 1000 volt limit on the carports. So that's something that you need to just be aware of and be thinking of. But for ground mount systems, very obviously not on a building. And what code says is that if the system voltage does not exceed 1500 volts, it's not required to comply with parts 2 and 3 of Article 480. So it's not saying you can't go greater than 1500 volts. It's just saying that if you are 1500 volts or less, or don't exceed 1500 volts, then those 2 parts of Article 480 you don't have to comply with those. And so that's, to say you could go find a 5 kV, a 5000 volts inverter and PV modules in a system. If you could find those components, nothing to say you can't build a higher voltage PV array. But because of currently available equipment, just the way things, what's available, 1500 volts is really a working limit that we have for our systems by and large. So the other thing that I wanted to talk about as it relates to this 690.7 and 690.8 are these sections that talk about calculations. And in 2017, there were some changes, 690.7 specifically. There were some changes about how to do the calculations. And so previous years for multi-crystalline modules, which are by and large the most commonly used modules, we had to do calculations, hand calculations to figure out adjusted voltage values. There's always been a table in code to reference as well. In 2017, the language changed up a little bit, and they said, you can do the math if you want, you can use the table if you want, either way is fine to calculate your adjusted system voltage. And I'm not going to get into those calculations here. We've got lots of resources we can supply for you if you need to, but just going to focus in on kind of the code language more than anything. And so what has changed in 2017 is this 690.7A3 for these systems that are greater than 100 kilowatts of generating capacity. And so, as mentioned earlier, knowing what does that mean, 100 kilowatts. And so we have this generating capacity name that we've attached to it as well. And so what you have to go do is you have to go see what do they mean by generating capacity. And so you have to go into Article 690, the definitions in 690, they talk about what generating capacity is. And that is the voltage, the power output of your inverter or inverters at 40 degrees C. Again, paraphrasing a little bit, but that 100 kilowatts is an AC value, and it's at the 40 degrees C temperature of the inverter. So pretty typical that inverter manufacturers, that's if they say it's a 60 kilowatt, 125 kilowatt inverter, it's typically listed at 40 degrees C. So you need to make sure that your PV array, in order to apply this new allowance, is over 100 kilowatts generating capacity, 100 kilowatts AC. So you may have 125, 135, 150 kW DC array onto those inverters in order to meet this requirement. And what this does is it gives us this allowance, and we can post this link in the chat as well, but there's a Sandia paper that's been written and code recognizes it as kind of an industry standard. It's a informational note, so it's not part of the code. So that's another thing if you're not super familiar with the way code is laid out or what the requirements are. There's a bunch of informational notes in code, and those are not part of the code language, so it's actually not enforceable. But it's a good reference, and it's a easy thing to reference to the Sandia paper, saying that this is one way to calculate our voltage values. And what you're gonna find, there's a few things you're gonna find. One is, so it's 100 kilowatts, so you're not gonna be doing this on residential, so you don't even have to worry about that if that's your bread and butter. On commercial buildings, it's probably not gonna matter a whole lot either, honestly, just because of rapid shutdown requirements at the module level and kind of what our voltage limitations are for those inverters to begin with. So really where you're gonna see this have the most play, potentially carports, but definitely ground mount systems, especially 1500 volt ground mount systems. And what's gonna happen is if you go through and read through that Sandia paper, work with an engineer, which by the way, the 690.7 does require that you have these calculations done by a professional engineer. If you go through and do those calculations, you may actually be able to have string lengths that are longer than what you would have otherwise using the standard calculation methods. And so you may be doing a 1500 volt system where standard calculations, depending on your location, maybe you could do 29 modules in a series string, but now maybe you can do, maybe it was only 28, maybe you can add another module, maybe you can even add 2 modules onto that string length, which if you're talking about thousands upon thousands of modules, making your string lengths just that much longer, you boost your voltage, your working voltage just a little bit, you move more power with the same size wire with less current on the system overall. It's just a great way to be able to save some money, eke out a few points in terms of the cost of the system. And on larger systems, for those of you involved in those really large systems, you know that every little bit helps and every little bit counts. So it's one way to help reduce costs of the system more than anything, moving the same amount of power with what maybe would be smaller or less wire than in previous versions. Now in 690.8, we move into circuit sizing and current calculations. And so you see, and there's two references there, the exact same sections in 2017 versus 2020. There were some additions in there, so that's why we have a little bit of a change there. But in essence, it's the same type of concept. So again, we're still talking about generating capacity 100 kilowatts or greater, but there's an allowance to use that same Sandia paper that you can calculate your current, your circuit currents differently than the way we have in the past. Not saying you have to. You can continue doing your calculations the way you've done, the way that we all learned from John Wiles and Bill Brooks way back when. Completely fine to keep doing those. This allowance on these larger systems just gives you the ability to potentially size your wires smaller than what maybe you would have to do. So the requirements are that, again, that you're doing this with a professional engineer, you're doing some site-specific modeling, so you're looking at the irradiance values at your location, you're taking into account orientation, tilt, local weather patterns, all those kinds of things come into play in terms of what is the circuit current that I'm calculating now. And this allows you potentially to use values that are less than what the short circuit current value is for those calculations. So it's interesting, we're starting to see, being design firm, we're starting to see our clients request this and use this more and more. And again, it was a change in 2017. Kind of the market tends to follow what's going on in California. So California just, beginning of 2020 adopted the 2017 code. So we're starting to be able to put this into play. Not to say this hasn't been happening in other locations. It's just, we're seeing the most of the bulk of the work that we're seeing specifically happening in California. So we're starting to see these take place, starting to see these really integrated into system designs. And so it's a fun and interesting way of looking at the system currents that we haven't before. Now, the next thing I wanted to talk about is a brand new thing in 2020. So for those of you who haven't quite adopted it yet, you can look forward to this. For those of you that have, this may be something you want to look into and see, can we integrate this into our designs and our installations? And what 690.8a is saying is, it's a brand new section, so I'll actually read this for you so it can kind of, it helps to hear it out loud and to say it out loud to kind of grasp it. But 690.8A2 is titled Circuits Connected to the Input of Electronic Power Converters. So it's not unique to inverters per se. An inverter would fit that description or that definition, but it's circuits connected to electronic power converters. So in this case, that's exactly what an inverter is. And so the text of this new code section says, where a circuit is protected with an overcurrent device not exceeding the conductor ampacity, the maximum current shall be permitted to be the rated input current of the electronic power converter input to which it's connected. A lot of words, and it's easier when you're looking at it and breaking it down kind of one by one. But what this ultimately is saying, and I'll break it down a little bit more, but ultimately what this is saying is that the inverter is a current limited device. And so it's only going to allow a certain amount of current into the inverter that it can process. And the PV array is, well, it's also a current limited device, but we can supply more current from the array towards the inverter, at least in theory, what the ratings are. But the inverter will only draw what it can draw. And so what code is recognizing is that those circuits between the inverter and, in this case, the combiner box, we don't have to upsize those for what the PV array, that theoretical maximum capacity is. We can size them for the continuous draw on the inverter itself. So this is going to come into play. You couple this with those previous two sections I just talked about, you're going to be sizing your conductor smaller. You're going to be moving the same power as you were in previous code cycles with smaller wire, more cost effective. And again, we're not limited, in this case, we're not limited by generating capacity like we were in the last section, but the reality is this is going to be probably, you know, commercial applications are where you're really going to see this shine, and where you're really going to be able to use this quite well. But let's talk about the language just a little bit. So where each circuit is protected with an overcurrent device, so you see I'm really focused in on the inverter input circuit here, and so the output of that combiner box. So we have overcurrent device that's not exceeding the conductor ampacity. So we're making sure we're properly protecting the conductors. So it says the maximum current shall be permitted to be. So this is interesting language again. I don't have time to get into all these, but I do in the full 6-hour class. So this is permissive language, shall be permitted to be. It's not saying it has to be, but you're allowed to do it if you so choose. So the maximum current can be permitted to be rated input current of the inverter in this case, to which it's connected. So put some real numbers and some context on this, just throw some numbers out. So if that inverter says the maximum input current is 48 amps, you may build your array. Pretty common anymore is to oversize your array compared to the inverter AC output ratings. And so if that inverter can only pull 48 amps, but if you do all your calculations on short circuit currents and everything, and the array is operating or has a potential of 60 amps, previous code cycles, we'd have to size everything based on that 60 amp as our starting number. Now we can say if we're protecting those conductors properly, we can start at that 48 amps, so we can size our wires smaller. So that specific example, you know, we're talking relatively small wires, so it's not a huge cost difference, but you start building those up, or you start doing this many, many times over, it really starts to add up. So new code section, kind of fun, kind of exciting, and new ways of doing the calculations and doing our system currents. Okay, I'm gonna move away from this. This is actually, real quick, I have just this one slide I wanted to show because it is new in 2020. You've probably seen, if you're paying attention, there's some big news a number of months back, fires, failures being pointed to PV arrays. One of the areas that it's been pointed to has been these mating connectors. And so 690.33, this is a 2020 code reference, that we need to have the mating connectors be identified and listed for intermatability is the word that they use. So we have a lot of quick connects out there that will say that they are compatible with MC4 is one of the big manufacturers, and so let's say they're compatible, but they may not have been listed and identified for use with those connections. So, you know, unfortunately, one of the things that we have in our industry is we don't have a standard. We don't have, you know, we don't have one standard set of connectors that everybody can build to and test to and make sure that if you're buying from, you know, module has connector A and you buy connector B, that those two are guaranteed to fit together. That's just not the case right now. So need to make sure that the connectors are listed and identified for intermatability. And so that's something that should be paying attention to more and more, even if you're in 2017 code. Just because it's not there doesn't mean you shouldn't be paying attention. And so this was these two pictures I took from the exact same PV array. And so you can see the pins and the sockets were different even within the same array. So making sure that I'm not saying that these are not listed and identified, I'm just saying that you need to double check and verify as you are installing those. Excuse me. Okay, let's jump into 705. I've got 705.11 and 705.12. I will do my best not to run through these as fast as possible, but rather, but I want to make sure that we do give ourselves enough time to talk about or for some questions at the end. So bear with me here. So 705.11 is now in 2020 is a new code section, supply side source connections. And this image that we're showing you is one way to do a supply side connection. I'm not going to say it's the only way. I'm not going to say it's the way that's going to get accepted universally. And so for those of you who are familiar with and are maybe doing these connections, the thing that jumps out probably to most people is the neutral to ground bond. And where does that happen? 705.11 in 2020 does not give us that definitive answer that we've been all wanting and trying to get. And it's a topic that's fun to talk about with folks. And I've been in a room with a bunch of code nerds and late at night, have nothing better to do. So we start talking about supply side connections, basically round robin through the room, and everybody comes into the conversation with their opinion on that neutral ground bond, where it should happen, where it shouldn't happen. And then by the time everybody's talked, had their say, everybody's changed their mind 2 or 3 times. So it is not a consistent, it's not something that you're gonna get consistent advice or input from. And the AHJ is going to have their own ways of thinking about this as well. So this is a good way to, or one of those areas where talking with the AHJ ahead of time is, in my opinion, your best bet. Nonetheless, what we're showing you here is a way to do it. It's an accepted way to do it in a lot of places. And what we're doing is we are not bonding in the PV system disconnect, and we're running those conductors separate, and the bond is happening in the main panel. So I'll just kind of leave that there at this point. But that is one of the ways that you can do this. In 2020, there are some allowances requirements in terms of what code is calling for with these supply side connections. And so we do have this brand new section. It gets into much more detail than we've ever had. If you look in 2017, all it says is, yep, you can do it. Have fun, go for it. In 2020, at least we have a little bit more to hang our hat on, if you will, with these connections. And so the PV system disconnect, depending on residential versus non-residential applications, there's a limitation in terms of how far those conductors can be. 10 foot in residential dwellings is still in there. We have to have this overcurrent protection. Talks about the equipment needs to be 60 amp rated, conductor 6 gauge or 4 aluminum, 6 gauge copper or 4 aluminum. So there's definitely some more meat to this and some guidance on how to do this. One of the things that is specifically called out, which is good and important to point out, is on the connections that you're actually making, those supply side, those physical connections on the service conductors in this case, they need to be listed for the application. So whatever way you're making that connection, it needs to be listed for it. And this is not new, but as you know, we've been doing previously, you need to make sure that that you're not violating the UL listing of the panel. So if that's a meter main, for example, you can't just drill into bus bars. So you need to make sure that you are maintaining the UL listing of the equipment you are connecting to. So that's the other pretty big thing that I would say that you need to be aware of. Now, one of the things that comes up quite a bit are on supply side connections are these basically the 6-handle rule and the application of the 6-handle rule. So I'll walk through this, kind of jump through this, these code circuits here to walk through this. So the big question that comes up quite a bit is, so if you forget about the PV system and that PV system disconnect, or forget about the inverter and the disconnect for a second, you walk up to a commercial facility, more than likely. You do see these in residential applications, but most likely commercial. You walk up, you have a you have the grid, you have the CT cannon, you have a main distribution panel that has 6 handles in there already. Pretty common scenario, completely code compliant, not a problem at all. And so the question comes up is, I want to add a PV system on there, and I want to add this quote unquote 7th disconnect. I want to be able to tie into the service conductors inside that main distribution panel, but there's already 6 service disconnects. And so the question becomes, is that okay? And if you ask me, I'll say, yes, I do think it's okay, and I'll give you some code references and ways to do that. But as I learned very, very early on in my career, there's 3 opinions that matter when it comes to code and application of code. There's my opinion, there's your opinion, And then there's the only opinion that matters, and that's the inspector's opinion. So this is one, by all means, get permission. Do not ask for forgiveness in this case. If you were to install this system and you just cannot get the inspector to see it your way with the way the code, and as I view it, allows this connection, that's a very expensive change. And so very expensive and very hard. So that's one to get it cleared up ahead of time. But relatively quickly, I'm gonna give you some code references here, and if you have your book, you can flip-flop through the code and see this. But in 705.11, or if you're in 2017, it's 705.12, the code says, yes, you can connect a PV system to the supply side of service disconnecting means as allowed by 230.82 number 6. So 230.82, 230 is services, .82 number 6, just 82 in general is a list of equipment that can be connected to the supply side of service disconnects. Fire pumps, emergency systems, a number of other things. PV happens to be one of them. So it kind of dies right there if you don't know where else to look in code. So all of that code section is saying, yes, you can do this. But what people will quickly point out is 230.71, 230.71, that there's this 6-handle rule. And if you read it, if you read 230.71, indeed it says you can have 2 to 6 disconnecting means permitted per set of service conductors per 240.40, exception 1345. And so it's saying you can have these disconnects, you can have 2 to 6 disconnects for these systems as allowed in 240.40 in these exceptions. And so quickly jump over to 240.40, read through them. I'll save you the reading. It's exception number 5. And what exception number 5 says is that you can have these disconnecting means on the supply side of the service disconnect for one or several, it says actually, one or several systems allowed in 230.82. And there's your full circle, 230.82, go to number 6, PV systems. So the reading on that is you could actually have 6 PV system disconnects. You could have 6 fire pump disconnects. You could have 6 emergency system disconnects. You could go and up to a system and not have just 6 handles, but you could have quite a number of handles in order to disconnect all of the systems allowed on the supply side of these service disconnecting means. So not to say that's going to be a reality, not to say that's really going to happen. I mean, in most cases, you're going to combine all of your PV into a single disconnecting means anyway. So, but those are your references and how you can get there. Okay, I'm going to do feeder taps in 3 minutes or less, so we can get some questions in here. So feeder taps, this is what you walk into a commercial facility, you have the feeder, you have your main panel, and then you have a feeder going off to a distribution subpanel. Pretty common scenario. And what I'm finding, I did, when this code section came out, I was like, there's no way people are ever going to use this. It's like crazy. But as time goes on, more and more people are finding that this is exactly what they want to do. They want to tap onto those feeders. This is a legitimate tap because it is a feeder tap. The previous section, supply side connections, those are service conductors we're getting on. They're not feeder taps. And so there's a big differentiation there. But in this case, we are connecting onto a feeder. And so depending on the exact location or exact system type, you may want to do this. And so what you have to be aware of and cognizant of is as soon as you add this PV system, you need to be looking downstream. You need to look at the sources of current and the conductors and the panels downstream of that point of connection. So in this case, before we added the PV system, we had a 200 amp breaker, we had a 200 amp panel, everything's honky-dory, no problem. You add a 100 amp or an 80 amp inverter, so it's 100 amp continuous. So now all of a sudden, downstream towards that distribution subpanel, I have potential of 300 amps of power, 300 amps of current, 200 from the grid, 100 from the PV. So from that feeder tap towards the loads, you would have to upsize all those conductors, you'd have to upsize that panel, kind of a pain in the butt, so probably not really gonna happen. towards the towards the utility, it's not a problem because the maximum current that you're ever going to get on that is 200 amps, and that's if the PV system was doing nothing middle of the night and the distribution panel was pulling a bunch of power. You'd get 200 amps flowing that way, but it was designed for that, not a big deal. The opposite end is if there were no loads and the PV system was kicking butt, then it would be sending 100 amps back towards the utility. Again, not a problem. So it's that downstream section of conductor and panels that you have to be really careful of. So one easy, quote unquote, easy way is put overcurrent protection right after that, that feeder tap. And now, still, under no circumstances can that distribution subpanel pull more than what it's rated for, that 200 amps. So you protected the wires everywhere. It's one good way of doing it. Another way of doing it is probably a more realistic way is if that tap, if that new set of conductors, or not new set of conductors, but the conductors with the two sources of power on it is less than 25 feet or less to that subpanel, you could put in a 200 amp main, protect those conductors, protect that bus bar. Everybody's happy. So we're able to properly protect that. So again, this is not a super common way, but I've been seeing it more and more in terms of systems that we're seeing out there. So, and I know I ran through that last bit fast, even though I said I was going to try not to, but I wanted to leave us a little bit of time. So, so with that, that's the kind of the quick teaser for NABCEP. So yeah, if there's some questions, we can go through those now. And then of course, thanks for your time, really appreciate it. And if there's any, general questions later on, or if we don't get through all these questions right now, we'll be sure and reach out to you folks after the webinar.
All right, thanks Ryan, that was great.
I feel like I was like speed talking through that last.
Yeah.
I don't know if anybody's watched Hamilton. They like have some incredible number of words per minute, and I just kind of felt like I was doing that there at the end. So apologize for that.
No problem. Well, so you guys can actually go back over some of those finer points, because we will be sending out an email to all of our registrants with a link to the recorded session. And so know that you'll have that. And also, as a reminder, this is, since we are a NABCEP's training provider, this webinar actually counts as a 1-hour credit. So that's also a very handy thing for us. And so with that, we have a couple questions that we'll go through. And the first one is about the integrated DC disconnect on those inverters, and if that can count towards the PV system disconnect, or if that can be identified as the PV system disconnect.
Let me go back. I'm gonna go back to all the way to that. So this is 690.1. I'll go to this simple system. So the question is, can the integrated disconnect act as the PV system disconnect?
Yeah.
So in general, I would say no. And the reason being, again, the way I like to look at it is, are we disconnecting all of the equipment required to convert solar to electrical energy? And so if you're using that integrated disconnect, you haven't isolated the power source. You still have conductors that are hot inside that inverter. Yes, you have stopped the power flow. Yes, the system will shut down, but that's you still have pieces of equipment that haven't been isolated, haven't been disconnected from all other sources of power.
Okay, simple enough. Our next question is about actually the definition of generating capacity of a PV system. Okay.
So that one was 690.7 is where that comes up. And that is, I'm gonna look real quick. I have my code book open, make sure that, yes. So it is just verifying. It is a new definition in 2017. So 690.2, and it's a brand new definition. So it is, since I do have it right here. So make sure, because I did paraphrase it earlier. So this is actually good. Yeah, see here, you always read your definitions and make sure you get it right, because I paraphrased it. I think I got it right in the paraphrase, but the definition is the sum of parallel connected inverter maximum continuous output power at 40 degrees C in kilowatts. So it is, if you have multiple inverters, it's the sum of the inverters. So AC output at 40 degrees C is what that generating capacity value is.
I like it. Nice and simple. Okay, great. Our last question we'll go over today, unless any more come up, is what about readily accessible when it comes to the PV system disco, the disconnect? Does it have to be outside?
Maybe. Just had this conversation come up last week with a friend of mine. So back to the PV system disconnect in 690, I want to say it's 13 or 15. I'd have to go back and look. It does talk about the PV system disconnect needing to be readily accessible. And so again, we'll go read definitions. So if you go to Article 100, accessible, comma, readily, they talk about what makes a disconnect readily accessible. And in 2017, actually, there's some language that got added, some clarification language that talks about not needing to use it. So it has to be accessible. You have to be able to basically walk right up to it without the use of tools to get to it. But they actually specifically call out keys as not being a tool. So, and the ready access to the equipment is to whomever needs that ready access, presumably a homeowner if this is at a house, or the technician that, you know, the building engineer tech that needs access to this. So this is not necessarily an emergency requirement, but it's just ready access for maintenance and serviceability. And so behind a locked door is considered readily accessible as long as you don't have to pull a ladder out to, once you're there with it, you don't have to pull a ladder out, move a bunch of stuff out from in front of it, so there is the dedicated space around it. So you don't necessarily have to have it outside. And the reason why I say not necessarily is 690.12, rapid shutdown, which I kept saying we weren't going to talk about, but I seem like I talked about it plenty. There is a requirement on residential dwellings that the rapid shutdown initiation device is outside, is readily accessible and outside. So there is that requirement. And in a lot of cases, the PV system disconnect could also operate as the rapid shutdown initiation device. So you're kind of getting the 2 for 1 in that sense. So depends on the installation, depends on the exact location, but it doesn't always have to be outside. So inside the garage would be a completely legitimate way for a place to have that PV system disconnect.
I think that's a great question, because when you get into rapid shutdown, there's very specific requirements about where those have to be.
Right. And it does say initiation device. It doesn't say the PV system disconnect. It just happens to be that in a lot of cases, yes, loss of AC power will initiate the rapid shutdown to make it easy. So you could use it for that. Doesn't say you have to, but you could.
Great. Well, that's super helpful. We did have one question come in about basically the NABCEP credits and how they will get those. And that's a good question, actually.
I believe that's being a NABCEP, it's kind of funny. I love to say how I've been involved with NABCEP for so long and been doing these. All the CE credits I've always done have been part of the conference, and so they've just handled those. My understanding is that you know, we will send out an email, you know, follow-up email that you've been here, and so those are self-reported, but I don't want to say that for 100%. And I know Sean was kind of dual purposing here, so he may not actually be listening right now. But I believe that is the case. It's a self-reported thing, and you'll have the email to show that you were here, that you did take part in the class.
Yeah, and we'll find that out and include that information in the email you'll get for
Perfect.
Attending this session. So we'll get that one sorted. Great question. Well, that's pretty much it. We're pretty much at time, and want to honor everyone's time as everyone is really busy these days. And so basically, thank you so much for joining us. As Ryan mentioned a couple times, this is a shorter presentation as a sample basically of our longer 6-hour course. And if you have any questions for Mayfield specifically, you can email us at hello@mayfield.energy. Or if you're actually in particular interested in our technical services line, you can also email us at technical@mayfield.energy. Yep. And with that, I believe we are done.
Great. Thanks, everyone. Appreciate it.
Thanks, Ryan. Everyone have a great day.